I'm in a pretty unique position where I have two vacuum tube computers in this room. I have this one, the UE1. This is a homebrew vacuum tube computer that I've been building from the ground up for a couple of years now. And then I have this one, which is the Bendix G15, a full-fledged vacuum tube computer from 1956. And both of these machines are absolutely epic. However, neither of these machines currently work. They're close, but not quite there. And I really want to see both of these going before the end of the year. So every other project in this room is on hold because it's tube computer or bust here at Usagi Electric. We are not going to let up until both of these machines are doing something pretty exciting. And actually, Lloyd is coming down on Friday to help me dig into this G15 yet again. And I'm really hoping that we're going to see it execute its first instructions this coming weekend, which you guys will see the next video in the coming week after that, because I got to edit all that stuff up. So that gives me until Thursday to shift focus and really hunker down and get some more progress done here on the UE1, because we have a very long road ahead of us with this machine. In the previous episode, we built that really cool tape reader and it pulls tape through just fine, but we haven't actually seen it produce any data. So that's what I want to focus on today. I want to try and see some squiggly lines on the scope coming out of the photodiodes on the paper tape reader. And I think that's going to be a pretty arduous journey because we got to make a lot of stuff and adjust a lot of things. And well, we got some work to do. So let's just get into it. In the previous episode, we made this. This is my paper tape reader. It is hilariously steampunk looking and incomplete. We got a lot more work to do on it, and that's what we're gonna do today. But before we do, you guys left a ton of excellent feedback and questions in the previous episode, and I wanna take a minute to address some of those questions. But I think in order to understand why I made the design choices I made on the paper tape reader, we need to take a step back and understand some of the design choices that we made for the UE1 as a whole. So what is it that we're building? Well, we're essentially building the vacuum tube version of this. This is the minimal ICU system as outlined by Motorola in the MC14500 handbook. The MC14500 is a 1-bit industrial control unit, and I didn't like the logic unit that they had in it, so I changed it and I put in a full arithmetic logic unit with a carry register so we can do addition and subtraction. But other than that, the architecture is pretty much identical, no change there. So both the UE1 and the minimal ICU system are 1-bit based machines. And because of that, we have a pretty interesting system layout here. You can see we've got the UE1 CPU on the left, and we're using the WRT or write signal output by it in combination with a 4-bit memory address to access either 8 bits of random access memory, a loopback of the result register, 7 bits of external input, or 8 bits of external output. And when we combine that 4-bit memory address with the 4-bit instruction for the CPU, we get a total of 8 bits. So one instruction is 8 bits in total, and it just so happens that paper tape, well, 8-level paper tape has 8 bits per column. So we can use this as our read-only memory that contains our stored program. This actually raised some pretty interesting questions, I think. A lot of people were very curious about why I was just sending the tape through without actually stopping on each individual column to read that column. And the answer to this is twofold. The first is that the UE1 and the Motorola MC14500 are pretty unique in that they execute a single instruction per clock cycle. More complex CPUs will read an instruction in, and they'll take multiple clock cycles to get through that instruction. But for the UE1, one instruction is 1 clock cycle. How is that even possible? Well, the way it's designed is that everything that has to do with setting up the instruction happens on the rising edge of the clock, and then we latch all of the results in on the falling edge of the clock. And because all we need is a single clock pulse, we can actually make use of the 9th hole on 8-level paper tape. And that 9th hole is the tractor feed in the center. And you'll notice that that hole is about half the size of all of the other holes. So what this means is that all of the data will come over the photodiodes before that center tractor feed hole does. So as long as we amplify it well enough, the data will be stable and we'll have a clean clock pulse before the data becomes unstable. So that means that everything on the CPU can happen without needing to stop on a specific instruction. And actually, I'm not smart enough to have come up with this concept on my own. This is exactly how Bendix does it on the G15. Now, the next question that a lot of people had was, why don't I set it up so that the tape can go forward and backwards? And that's actually very, very rare for paper tape systems. I think only some like unique industrial control applications used that. But because we have a unique problem, that's actually a really interesting idea to find the solution. The problem is that how do you know where you are on the paper tape? Each column only contains an instruction. It doesn't have an address or anything like that associated to it. And actually, the MC14500 ICU and minimal ICU system is set up such that you can build complex programs with branching logic without knowing where you are in the program. You don't need a program counter and you don't need the ability to jump. We're doing this by using the input enable register and the output enable register. So each instruction is executed every single time, but whether the IEN or OEN registers are on or off, we are masking input and output out of the system, and we can effectively turn instructions that we don't want to execute into NOPs, into no operations. So by doing this, we can create a tape loop. Then we can effectively skip over blocks of code. But if we want to jump back to that block of code, well, we just wait until it comes back around on the loop. So those were the two big questions that I think you guys had, and hopefully I've addressed them successfully. So what are we working on today? Well, we're digging right back into this. The capstan here is fine. It's working perfectly fine. And yes, I realize that there should probably be a bearing where the brass and aluminum contact each other, but this thing's probably gonna have like less than 100 hours of uptime for its entire life. So if that proves to be a problem, I'll deal with it then. But for now, I think it's gonna be fine, except for the fact that I think the top side of our capstan here needs a little bit of extra support. So I'm gonna try and make up something there that supports that today. And then next, I want to focus on these tensioners over here. These are absolute garbage. They need to be pulled out and replaced. You guys had a lot of great comments. I'm just going to see if I can come up with something. I don't really have a good idea at the moment, but we'll see what happens. But the big one that I want to do is I want to build the PCB that sits on the back side of these photodiodes that solders into all the photodiodes and then has a connector on it that'll ultimately go up to the rest of the system, because then we can put 24 volts and ground into that connector and we should be able to pull the tape through and see if the photodiodes are flipping and flopping. But in order for them to do their thing, they gotta have a light source. So I need to build a light source that sits on this side of the photo tape reader that puts a bunch of bright light right through there, but not so much that it shines through the photo tape. So we got a bunch of work to do. Let's get to it. Let's start with making the capstan support. I'm going to make it out of this just steel rod that I found laying around, and I need to drill a hole in the end of it, so I just grabbed a massive hammer, set it on the vise, and just swung away. It was a bear to keep it from warping too much, but in the end, we got a pretty nice flat spot. And this will allow me to toss it in the drill press next and punch a nice hole through. Then it's over to the metal brake so I can put a bend in it. I need to ultimately shorten the rod up, flatten the other end, and then put one more bend in it. But in order to know by how much and where, I'll have to mock it up first. And after a rinse and repeat of the first half, as well as a little polishing, that is a mighty fine looking capstan support, if I do say so myself. It's nice and solidly mounted, and the capstan is now super rigid if it needs to be. So next, let's take care of those atrocious tensioner arms. I'll remove the old ones first, then slot a new bolt through, cinch it down tight, and then get a measurement of how tall the tensioner needs to be. Then I'll transfer that measurement over to this 1/2-inch piece of copper tubing. A proper pipe cutter makes quick work of slicing through tubing like this and leaves a really clean edge. And this is just plumbing stuff from the local hardware store, but I think it's gonna work great. I'm dropping on oversized nuts here to help locate the copper tube correctly over the center. And later off camera, I cinched down a lock nut on the oversized nuts inside so they wouldn't rattle around. Next, I think it's time to make that PCB for the photodiodes, but something ain't right here. And yeah, that's not good. Software failure, give this exact message to your mill power distributor. Well, that ain't happening, but let's think about this a moment. It's been about 6 months since I last cut a PCB, and in that time, the software I used to generate G-code from Gerber's, FlatCam, has been updated a few times. For some reason, I have no idea why, it now adds this block of code to the G-code, and something in here is causing my mill power mill to crash. So let's break it down. The first code is M5, which means stop the selected spindle. Now, our mill doesn't have a CNC spindle control, it has just X, Y, and Z. However, we do get past this instruction when trying to run, so I don't think this is our problem, although it's not great to have this in there. The next instruction is G00Z15.00. G00 means it's time for rapid movement. And this one is telling it to move the Z-axis to plus 15 millimeters. And then we follow that up with another G00 to X0, Y0. Again, another rapid movement, and it's telling it to center the X and Y axis over 0. Here's where I think maybe we're starting to run into some troubles. The T1 instruction is a prepare to change a tool instruction. But the next instruction, M6, is a tool change instruction. So I think either this one or the instruction after this one is our culprit that's causing the whole thing to crash. And obviously our mill doesn't support tool changes, so this one might be trying to do something that isn't possible. And then the next instruction is M0, which is a program pause instruction. Both M0 and M1 are pause instructions, but I don't know if our mill supports one or the other or both or neither of these instructions. But either way, none of this stuff is needed. I'll already have the right tool in place and the spindle clear, so I can delete this entire block of code and it should continue to work just fine. And indeed it does. Looks like we're off to the races here. Our isolation cuts are slicing out the area around traces to isolate them from the rest of the copper. It should do 3 isolation passes with 10% overlap. At the depth it's cutting with a 60-degree V-bit, it should be cutting a width of 0.331 millimeters on each pass. That means all in, I should get 0.92 millimeters of isolation around each trace. In practice, of course, a lot of things make that isolation smaller. Through-hole pads, for example, eat up a bunch of real estate. Either way, the program seems to be chugging along just fine, and the PCB is really starting to shape up. And my favorite part of machining PCBs, especially when compared against etching PCBs, is that in order to drill all the through holes, I just do a quick tool change to a 0.9 millimeter drill bit, load in the next program, and hit go. It drills every single through hole for me perfectly every single time. On a small PCB like this, that's not really a huge deal, but on some of the larger PCBs I've made, they have like 1,000 through holes on them. That would be a nightmare to try and drill on the drill press. Also, I can do just one more tool change to a 1.5 millimeter end-to-mill bit, hit go, and then it cuts the outline of the PCB perfectly. This is especially brilliant for weird or uniquely shaped PCBs like this one. Once the end-to-mill finishes its thing, the PCB just needs a bit of cleanup. For me, that usually means a wire brush and a trip to the sink. But look at how well that PCB turned out. That's awesome. Before I can solder it up though, I need to figure out how I'm going to mount it to the aluminum plate. I don't have a perfect bracket on hand, so I'll modify a different one. A chop like this with the cutoff wheel leaves a sharp and jagged edge, so I usually spend some time with a file on brackets like these, rounding out the corner and getting a much smoother finish. Next, I'll populate the PCB with the resistors and jumper wires that need to be soldered in place. Then I'll pull out the trusty Weller soldering iron and melt some metal. Even for such a small PCB, there's still a surprising amount of solder joints. In order to solder the photodiodes on, I need to go through and reorient each diode in the correct way, so I don't solder any end backwards. This was an extremely tedious and frustrating job, but I got there in the end and got them all soldered in place. Next, let's work on that light source. I want to make a bracket to hold the light bulbs out of this chunk of aluminum, but that means I need to bend it, and bending 6061 aluminum is a bit of a nightmare. If you don't anneal the aluminum, when you try to bend it, it'll stress fracture and just fall apart. You can anneal the aluminum though by using a torch. Get it nice and hot and then carry it over to the metal brake and give it a bend. The good news is that it didn't fall apart and feels plenty strong, but you can still see some stress fractures on the surface. Talking with my good buddy John though, this actually isn't that bad for 6061, so let's just keep on rolling here. To clean up the bend marks and get rid of the small stress fractures, I'm going to sand the whole thing rigorously with 400 grit, then 600 grit sandpaper. This should give a nice finish and clean up any unsightly marks, but I want the inside to be more reflective than just sandpaper can give, meaning it's time to fire up the polisher again. And after less than 5 minutes on the polisher, look at the finish here. The sanded portions look great, yeah, but the polished portion looks almost like a mirror. That's gonna be awesome. And I'm gonna use 2 small 9mm bayonet base bulbs for my illumination. The double bulb setup helps ensure an even spread of light across the total width of the paper. But the bulbs are quite weak. They're just 1 watt each. These were all I had on hand. I definitely need to upgrade these to 3 watt or 5 watt bulbs, and I have some on order. But for now, we're gonna stick with the 1 watt bulbs. The final step is figuring out how to mount the big power resistor for motor speed control. I'm thinking right here along the top is nice and out of the way and it won't get caught on the paper in any way. And I do want it to be rubber isolated. So a long piece of all thread is going to go through the center. Then 2 brackets are pressed up against beveled faucet washers. These rubber washers isolate the ceramic from any metal. I'm not worried about shorts or heat transfer so much as I'm worried about chipping or breaking the ceramic. This solution covers all the bases though. And the finished product is absolutely stunning. We have a hilarious hodgepodge of metals going on here. The majority is made from aluminum, but there is some steel, copper, and brass in places. I think all the different metal colors complement each other really well though, because it looks awesome. I'm really happy with that. Here we go, finished product. It looks amazing, but I have genuinely not tested it at all. I have no idea if the photodiodes are even going to be receiving light. I don't even know if the lights are going to turn on. I think I've got everything wired up correctly, but this is genuinely the first time I will have tested it. I've got a scope set up here. We're checking 2 signals. One should be the clock and one should be just a random data signal in the middle of it because I've got a little temporary harness set up. I've got 2 vacuum tubes here set up as inverters, pretty much just duplicating this schematic here that we figured out 2 episodes ago. But, well, what we're hoping to see is squiggles on the scope here. What I'm expecting to see is absolutely nothing because it's so many moving parts. There's no way it's just gonna work on the first try. If it feeds tape still, I'll be happy. So we'll set the bar low here. Here we go. Here goes nothing. Negative 12 volts coming on now. It is feeding tape. The lights have come on. We aren't seeing any squiggles though. Like nothing at all. Not unexpected. Not great though. So we got some more thinking to do. At least it fed tape though. That's pretty awesome. Okay, the photodiodes appear to be photodioding. The problem I think was coming from the biasing of the 2 6AU6 inverters over here that are amplifying whatever the photodiodes are seeing. The 220K, 330K resistor divider that I had in there was incorrect, so I pulled that out and I put in some 500K potentiometers, and I was just doing some simple testing by just putting a piece of paper in front of the diodes and off, and I think I've got those adjusted correctly. I haven't tried sending actual paper tape through yet, so let's give that a shot. I want to see something happening over here, so here goes nothing. Yes! Look at that! We clearly don't have the clock correct, and it may just be that I'm on the wrong pin, but that's, we saw squigglies! We saw squigglies! Yes! After a little more tinkering, we're getting close, but we're still not quite there yet. Let me set it up to run here. I've got a little paper tape loop going on, which loops perfectly. That's excellent news. But if I get this little paper tape loop here circling by, you can see that on our scope here, yellow is data. That looks great. Purple is the clock, and that looks like utter garbage. Does not look correct at all. So let me stop this here right quick because it is pretty noisy, but I think bevel gears and those kind of motors are just going to be noisy. So let's take a look at the evidence here. I went through and checked all 8 of the data bits, and 7 out of the 8 are squiggling just like they should be. I didn't check them with amplifiers on them, I just checked the photodiodes, but yeah, they're all squiggling like they should be, except for bit 0. Bit 0 is just totally flat. Now, also, we have a major problem with our clock. The clock never looks like a clock. There's a lot of noise on it. It looks like garbage, if we're being honest. And the clock was going to be a problem anyways. I knew this going into it. Bendix knew it when they built the phototape reader for the G15. And that's because the hole for the clock is so much smaller. It's half the size of all of the data holes. So that's just half the amount of photons that are making it to the photodiode and happening at a much faster pace. So we knew that was going to be an issue. Bendix solved it by biasing their photodiode to an extra 5 volts beyond what they biased all the other photodiodes for. So we might have to do a little something tricky there. So we've got multiple problems going on here, and I'm going to need to dig into it in more detail. And I think doing it with this kind of random tape that I found, I have absolutely no clue what the data is, and it doesn't help us for diagnosing and troubleshooting this thing. So I think I need to punch a tape that has a very specific pattern, maybe like 101010 for bit 0, then 11001100 for bit 2, and so on down the line. Unique patterns for each bit, so that way I can sit the thing on a loop here, and I know what pattern I'm supposed to be seeing on the scope, and if I'm not seeing that pattern, or if I'm seeing a different pattern, I know that I've got an alignment issue, or I've got a balance issue, or I've got something else going on. So trying to troubleshoot with random data is never going to work smoothly. So I think the next step is to try to figure out how to punch tape. Now, I know that we've all been watching me build a paper tape reader from scratch, and I am absolutely positively not going to build a paper tape punch from scratch. I am crazy, but I am not cruising for a bruising here. So I actually have a paper tape punch. It is a facet punch, and we're gonna bring that one back to life. It's in pretty rough shape, but I think we can bring it back to life. It runs off of serial RS-232, so I should be able to send it a serial signal and punch out tape in whatever orientation or pattern that I want, and we can set it up as a paper tape loop and get to testing. But enough of this works right now that I think we can continue on with the build, and we don't need to tear it apart. We don't need to go, this was a prototype, tear it down, build another one. This one I think is going to work perfectly for the machine. That is an absolute win in my book. We just have a little more tweaking to get it across the finish line, but I think it will definitely get there. So I want to thank you all so much for watching, and I hope to see you in the next episode because we're going to be on the Bendix G15, and that's going to be real exciting.